We are diving straight into CLAP, Contrastive Latent Action Pretraining for Learning Vision Language Action Models from Human Videos.
And this paper, it really tackles what's arguably the biggest scaling challenge in robotics right now.
The data problem.
Exactly. The core constraint is data. These big generalist vision language action models, or VLAs, they need just massive amounts of varied data. But high quality robotic manipulation data, it's extremely scarce.
Especially when you put it up against the ocean of human videos out there, things like the Ego 4D dataset.
It's not even a comparison, and the old approach of trying to learn from that video data just runs into this problem the authors call visual entanglement.
Right, where the model gets confused by things that aren't the action itself, like a change in lighting or the background shifting.
All that irrelevant visual noise. So CLAP's solution is, well, I think it's really elegant. It's contrastive latent action pretraining. It creates a shared language by explicitly aligning the visual information from human videos with a quantized, physically executable action codebook from the robot.
And that shared language, that alignment, is what lets them build this really clever dual policy framework.
It is. You get two policies. First is CLAP-NTP, which is your high-level planner. It's great for understanding instructions and, long-term reasoning.
And then you have CLAP-RF, which is the specialist, the rectified flow policy that handles the actual high-frequency, precise motor control.
And it is fast. We're talking 183 milliseconds for inference.
The results really seem to back it all up. A 61% mean success rate on some really tough, real-world tasks.
That's state-of-the-art, right? It's blowing past baselines like Pi0 and UniVLA.
It is. So that's the punchline. Now let's unpack how they actually built it.
Okay, so let's dig into that bottleneck you mentioned. The trend is obviously these big generalist VLA models that use LLMs for semantic understanding. But just how bad is that data gap between robots and humans?
Oh, it's massive. I mean, think about it. When you get data from a robot like the Astrobot S1, it's perfect. It's labeled precise, the kinematics for all 14 degrees of freedom at every single moment. But it's expensive, and you can only collect so many scenarios.
Exactly. Now compare that to billions of minutes of human video on the internet. It's incredibly rich in context and diversity, but it has no labels, no kinematic states you can just feed to a robot.
And that's the wall that the old latent action models, or LAMs, would hit. They just look at a before and after picture, basically, and try to guess the action.
Right. They're trying to infer action from pure visual change. And if that visual representation isn't grounded in what the robot can physically do, it gets polluted. It gets entangled.
So if you're trying to teach it grasping, it might learn that the pattern on the carpet is part of the action.
Precisely. And that skill just won't transfer. Not to a new room, and definitely not from a human video to a robot.
So CLAP's mission is to force this isomorphism.
Yeah.
A perfect mapping where a human action in a video translates directly to a robot command.
Exactly. And to do that, you first have to define the robot side of the equation. You have to build its physical language.
Which brings us to the first big piece of the methodology, the semantic action quantization, using what they call an ACT VAE.
Right. So you have this continuous 14-dimensional stream of data from the robot, all the positions, orientations, gripper states. How do you make that discrete?
You build a dictionary.
You build a dictionary. They use a transformer-based VQ-VAE, that ACT VAE, to translate those continuous movements into discrete action tokens. It's basically learning the robot's vocabulary.
I'm guessing there's a trade-off there. A small vocabulary might not be expressive enough for fine motor skills, but a huge one would be inefficient.
You hit the nail on the head. And they solve that with a rate distortion analysis. They find that elbow point on the curve that perfectly balances the compactness of the language with the fidelity of the control.
And once they find that sweet spot,
that codebook, that dictionary of actions, gets frozen. It becomes the absolute ground truth for everything the robot can possibly do.
Okay, so if the ACT VAE gives us the robot's dictionary, the next step has to be teaching the vision model how to speak that language. This is the VDVAE part, the cross-modal dynamics alignment.
Correct. The VDVAE looks at a visual transition in a human video frame T to frame T plus H, and its entire job is to predict which action token from that frozen robot dictionary must have occurred.
And this is where they finally tackle that entanglement problem head on.
They do. The encoder in the VDVAE is really clever. It splits the visual information into two streams.
One for the action, one for the noise.
Exactly. You get ZVA, the action-relevant latent, and ZVI, the action-irrelevant latent, which is supposed to capture all that junk like lighting changes and background motion.
And here's the magic, right? The contrastive grounding.
This is the core idea of the whole paper. They take that action-relevant visual stream, ZVA, and they quantize it using the frozen robot dictionary. Then they use a contrastive loss SIGLIP specifically to force the continuous visual latent to align perfectly with the continuous action latent from the robot's world.
So for our listeners, what does that contrastive loss actually do? Is it like a filter?
It's a very powerful filter and alignment tool. Imagine the model sees a hand closing around a key in a video. It generates a visual representation for that, ZVA. The contrastive loss then powerfully pulls that representation closer to the close gripper token in the robot's dictionary, and at the same time pushes it away from all the other tokens.
So it learns that the reflection in the key isn't part of the action because there's no make a reflection token in the robot's dictionary.
Precisely. And to make sure, they also penalize the other stream, the noise stream. They apply L1 regularization to ZVI, which encourages it to be sparse, to be as close to zero as possible.
So you turn up the volume on the action signal and you mute the noise signal.
That's a great way to think about it. And that single step is what creates this disentangled representation that lets them generate reliable action labels, pseudo-labels, for any human video they want.
It's a really fundamental solution. But, okay, once we have this unified latent space, they make a point that just training one big model on it isn't the best idea, which leads them to this dual policy framework. Why two policies?
It's the classic trade-off in robotics. Reasoning versus reactivity.
Thinking versus doing.
Exactly. A big autoregressive model is great at planning, at understanding the what, but it's slow. It predicts one token at a time. For the how for fast physical control, you need something much, much quicker.
So for the thinking part, we have CLAP-NTP, the next token prediction policy.
That's your high-level planner. It's built on a foundation VLM, Qwen3VL4B, and its job is to predict the sequence of subtasks and the discrete action tokens. It's trained on both the robot data and all those pseudo-labeled human videos, so it's really good at following complex instructions.
And then for the doing part, the pure speed, we have CLAP-RF, the Rectified Flow expert. That's the one that hits that 183 millisecond inference time.
Right. Its whole job is low latency, high frequency control. It distills the policy into a continuous action expert using a diffusion transformer, or DIT. So we're moving from predicting discrete tokens to generating a smooth, continuous trajectory.
Okay, but wait. How do you make sure that this fast, low-level muscle model doesn't just forget all the important context from the big VLM brain model?
That is a huge challenge. And they have this fantastic mechanism they call knowledge insulation. The DIT, the action expert, needs to know what the VLM decided the goal is, so it queries the VLM's context, the key and value cache using cross-attention.
But if you train the DIT, don't the gradients flow backwards and mess up the VLM?
They would, and that's the last thing you want. You can't have these noisy, high-variance action gradients corrupting the incredibly valuable semantic knowledge in your giant pre-trained VLM.
So they use a stop gradient.
A stop gradient. It creates a one-way street for information. The VLM tells the DIT what to do, but the training gradients from the DIT stop dead at the boundary. It insulates the brain while giving the motor cortex full access to the plan.
That is a very clever solution.
Yeah.
And the DIT itself is trained with a rectified flow objective.
Yes, which makes it very fast and parallelizable. It just learns to predict the vector field needed to get from the current state to the goal state in one shot.
And what about fine-tuning? To avoid catastrophic forgetting when they adapt this to a new robot, they use something called knowledge-matching regularization.
Right, that's their defense mechanism. It basically keeps a frozen copy of the original model around and penalizes the new model if its predictions start to stray too far. It anchors the policy to that solid, pre-trained knowledge base so it can adapt without becoming stupid.
Okay, so the whole architecture is built.
Yeah.
Let's talk about the real world. They use the Astrobot S1 dual-arm robot and a pretty demanding set of tasks.
Oh, yeah, it was a tough suite. They tested everything. Basic generalization on pick and place with unseen objects, long horizon planning with packing a doll, and some really hard contact tasks.
Like folding a t-shirt.
Exactly. Bimanual deformable object manipulation, one of the hardest things in robotics. And then a semantic reasoning task, making bouquets based on text instructions.
The overall numbers are really strong, that 61% means success for CLAP-RF. But I think the most interesting part is comparing the two policies, NTP versus RF.
This is where you see why they needed both. For the high-precision tasks, you absolutely need the speed and continuity of CLAP-RF.
The t-shirt folding task is the perfect example.
A perfect example. CLAP-RF gets a 40% success rate, which is double the 20% that CLAP-NTP got. Same thing with closing the lid on the doll box, a task that needs precise alignment. RF was at 70% success, NTP was at 60%.
So the discrete planner, NTP, is good at figuring out the steps, but its token-by-token nature just isn't smooth enough for fine motor control.
That's it. The discrete model is the strategist. The continuous model is the masterful execution engine. You need that split.
The results also show that the model generalized really well to new objects and was robust to things like changes in lighting.
Which really proves that they solved the entanglement problem. The model learned general manipulability, not just what a specific training object looks like. It learned to filter out the noise.
Which brings us to the final and maybe most important experiment. Proving this whole thing actually lets you transfer skills from human videos. The Make Bouquets test.
This test validates the entire premise of the paper. When they trained the model on only robot data, it completely overfit. It couldn't handle new flower combinations, less than 10% success. It just didn't have the semantic understanding.
So to fix that, they just showed it some videos of a human doing the task.
A small set of egocentric human videos, yeah. They use the VDVAE to generate pseudo-labels for those videos and then fine-tuned the model.
And that was the moment of truth.
It was. After fine-tuning on those human video pseudo-labels, CLAP-NTP successfully generalized. It could handle the new unseen flower combinations. That proves that this shared latent space isn't just a theory, it works. It can pull semantic skills out of human videos and put them directly into a robot.
So to wrap it all up, CLAP solves that core visual entanglement problem with this explicit contrastive alignment.
And then the dual policy framework very intelligently splits the labor. You have the big VLM brain for planning with CLAP-NTP, and a specialized high-speed motor cortex for execution with CLAP-RF. It's a huge step forward for using all that human data we have lying around.
It really is.
Yeah.
Which, looking forward, raises a really interesting question. If this works so well for a 14-duve action space for 2 arms, what are the limits here? Could you apply this embodiment-agnostic learning to something much more complex like dynamic locomotion or, say, a multi-fingered, highly dexterous hand?
That is the logical next frontier. The current ACT VAE codebook is a language for 2 arms, creating a new quantized vocabulary that could concisely represent the dynamics of a bipedal gait or a 20-degree of freedom hand without losing fidelity. That's an immense challenge. But the CLAP framework gives you the recipe. Define your physical language first, then contrastively align the messy real world to it.